Okay, hello everyone. So today we'll be looking at step 1, 2014 question 1. Okay, right. So the first three parts are hopefully the ones that relatively fairly straightforward. So part 1 just involving listing down a few numbers. So if you list down a couple of square numbers and then you can try to find the differences. And the answer you should get is 2 square minus 1 square is 3. 3 square minus 2 square is 5. 3 square minus 1 square is 8. 4 squared minus 2 squared is 12. And finally, 5 squared minus 3 squared is 16. Okay. Part 2, we need to prove that any odd number can be written as a difference of two squares. So bear in mind, from A levels, we know that we could represent any odd number by 2m plus 1 or 2m minus 1, say. And here, because we're talking about all non-negative integers. And so actually, if we consider the following, okay, and then so this should give you 2n plus 1, and so all odd number can be represented as difference of two squares. Of course, maybe write a bit more, therefore a bit more justification, but here is essentially an outline. Okay. Part 3, similarly, if we consider the number k plus 1 all squared minus k minus 1 all squared, okay, and then this should give you again 4k. So we can turn anything in the form 4k into difference of two squares. Okay. Part 4. Okay, so we need to prove that no number of form 4k plus 2 can be written as a difference of two squares. So here we have to essentially do this by exhaustion. So we need to suppose if we if we consider difference of two square, p squared minus q squared, which is equal to p plus q, p minus q, where p and q are, let's call it the natural numbers including 0. And so we really need to think about the cases arises if p and q are both even, both odd, or odd and even. Okay, so let's see. So if both are even, then we can say that p is 2m, q is 2n, again for some m and n. And so then we will have that p squared minus q squared is equal to 4m plus n times by, actually, I'm not sure why I did that. It's equals to 4 multiplied by some constant. Now we can see that 4k plus 2 is a number. 4k plus 2 is divisible by 2, but not divisible by 4. And so this number is divisible by 4. So therefore, if both of them are even, we cannot express the number. Well, if both p and q are even, then the difference between the square of these two numbers are not in the form 4k plus 2. Okay, and then similarly, suppose both are odd, then again with a similar setting, p 2m plus 1, q is less be 2m plus 1, and then we have p squared minus q squared is equal to let's see, 2m plus 1 plus 2n plus 1 times by 2m plus 1 minus 2m minus 1. This will give us 4m plus 2 multiplied by 2m minus n again. We have a take factor of 2 out from both brackets. We will get 4 multiplied 2m plus 1 m minus n. Again, a multiple of 4. Okay, and so again, this cannot happen. So if p and q are both odd, then the difference between the squares are therefore they are not in the form 4k plus 2. And then final case, we can just consider when p is odd and q is even, because we can just, the problem's symmetric, so we can switch around later. And so suppose p is odd, q is even, then we have p is say 2m plus 1, q is say 2n. Oh, I should say that we've been assuming that p is greater than q throughout this thing. So, well, let's say with log p is greater than q. Okay. And so you should obtain p squared minus q squared. This is equal to 2m plus 1 all squared minus 2n all squared. That is 2m plus 1 plus 2n times by 2m plus 1 minus 2n, which is 2m plus n plus 1 multiplied by 2m minus n plus 1. Okay, and actually we could have actually done this a little bit better if we actually just expanded a while without actually using the difference of two squares here. So this is 4 m squared minus n squared plus 2 m plus m minus n plus 1, which is 4 bracket m squared minus n squared plus m plus 1. Okay, so again, this is not the form of 4k plus 2, and so therefore, again, if p is odd, q is even, then this doesn't work either. Okay, cool. And so if you were to, you could also prove that p is even and q is odd, and the whole point there, you would just see a very similar result. Okay. Right. Now move on to the part 5. Prove that any number of the form pq, where p and q are prime numbers greater than 2, can be written as difference of two squares in exactly two distinct ways. Okay, so let's do that part first. Okay, so the first thing to think about is that, well, let's say pq is equal to a difference of 2 squared, which we can use our formula. We can write this. Okay, and then so this just comes to the case of really equating each of the factor to each of the factor of pq. Okay, so there are two scenarios. We can either have p is m plus n, q is m minus n. Okay, and if you solve the maths, well, if you do the maths, you should obtain m is p plus q over 2, n is p minus q over 2. Now bear in mind that both p and q are prime numbers, and the reason that this doesn't include the number 2 is that all prime numbers apart from 2 are odd. So if you add two odd numbers, you get even numbers, and so this p plus q over 2 and p minus q over 2 are in fact integers. Okay, and so one way to therefore express p and pq is going to be p plus q over 2 squared minus p minus q over 2 squared. That's one way. The next way to think about, well, we can actually split pq as pq times 1. Okay, so therefore, let's say pq is equal to m plus n, 1 is equal to m minus n, and so again, solving these two simultaneous equations, and so we should get m is p plus q, p times q plus 1 over 2, and n is pq minus 1 over 2. Again, p and q are odd, So PQ is even. Sorry, P and Q are odd. PQ is therefore also odd, and so PQ plus 1 and PQ minus 1 are therefore even. Okay, and so we can also represent this in the form of PQ plus 1 all squared minus PQ minus 1 over 2 all squared. Okay. Now, we can see that actually, the reason if, say if Q is 2 and P is not 2 but a prime, then a prime but not 2, I mean, and so then what will happen is that each of these numbers will become not an integer anymore. You will have some 0.5 in it. So that's why we cannot do the same if one of the P or Q is a 2. Okay. All right, final part. So the final part really kind of applies the technique we done for part 5 and doing it now for a more general number. For part 5, 675 is equal to some m squared minus n squared. So this is m plus n times by m minus n. Okay, so now we just need to think about how many ways can we write how many distinct ways without change of permutations can we express 675 as a product of two numbers. Okay, so well, we can firstly factorize 675, and if we factorize it, we should get 3 cubed and 5 squared. Okay, and so actually there are exactly 4 ways. Okay, oh sorry, 5 ways we can split this into different ways of timesing each other, and so this is equal to 135 times 5. This can be 27 times 25. This is also equal to 9 times 75. This is also 3 times 225. And the last one that might be the one that people might miss is 15 times 45. Okay, when you have a 3 times 5 and a 3 times 5, 3 times 15. Okay. Right, and then so we can use all of these results, and so for each of these multiplications, we should get one. We should get one ways to express 675 as difference of two squares. But in fact, then we can obtain an extra one by using this fact. Okay. Using the fact that PQ is 675, so there are actually a total of 6 ways to express it. And so so if you were to find all of them, I'm just going to list it down. They are 70 squared minus 65 squared. They are 330a squared minus 337 squared. 26 squared minus 1 squared. 42 squared, minus 33 squared, 114 squared minus 111 squared, and finally 30 squared minus 15 squared. Okay. Right. Thank you very much.